Sir, good evening.
Good evening, good evening.
Sir, good evening, sir.
Good evening, sir. Good evening.
Yes, sir. I made a host, sir. Yeah.
Okay, thanks. So, welcome back, friends.
Yeah.
Uh, okay, so good evening, friends. Hope you had a interesting and enlightening session yesterday, where we discussed the concepts of theory of constraints and some other very interesting concepts about how to deploy a strategy, and starting with the vision and mission of the organization, defining the strategy, and a very effective methodology where we map the strategy deployment in a very comprehensive and understandable manner. And not only comprehensive and understandable, it also shows the cause and effect relationship between various initiatives that we take. So, hope Thangaraj sir, Ajay sir, Praveen sir, Shweta ma'am, Meeraja sir, Palaniyappan sir, Ajay sir, hope all that was very clear, and we are going to make use of those concepts in our improvement initiatives, because it becomes, as a lean consultant, as a Six Sigma consultant, as a leadership change agent, it becomes very, very important to convince people why we are kind of introducing all these new methodologies, these new initiatives, because every new initiative will kind of face some resistance. Yes. Please come on, cameras. I am also very bad looking, so do not feel shy that you might not be all that camera smart. No, no problem. So the concept is that in addition to learning these academic tools, these concepts, technical concepts, academic concepts, we also need to learn as leaders how to bring people on our side, how to convince them. Because the core for a successful professional in this field lies in developing two specific competencies in the people, that we want to develop. Number one, competence. Number two, willingness. So I've got a very interesting metaphor for understanding this. There are typically four type of people. Number one, who are competent but not willing. Willing but not competent, neither willing nor competent, and certain people who are competent and willing. So obviously, we would like to work with, we would like to create understanding, we would like to create a team where people are not only competent, but also willing to contribute, willing to go that extra mile. And for that, we need to convince. It is not a bureaucratic setup. It is not a dictatorial setup where you go and dictate certain things that, okay, from tomorrow onwards, this is how things are going to happen. The idea for the modern management, for the successful management, is we shall be able to make people competent to identify and solve problems, and not only competent, but also willing. And for that, we need to convince them, we need to create that kind of interpersonal relationship, interpersonal bond, and that comes with celebrating small successes, respecting contributions from each and every individual. And therefore, I spend a lot of time on explaining why we need to map the strategy. My dear friends, today we are going to have a look, a very detailed look, a very in-depth look, because this tool that I am going to discuss today in today's panel discussion not in a monologue. In today's panel discussion, the concept that we are going to discuss is of value stream mapping. And I will start from the very foundational concepts, very basic concepts about the cycle time, takt time, lead time, throughput time, open, close, up time, down time, changeover time. So many concepts, all those are foundational, and it is extremely important that we understand the real meaning of all these terms. And based on the vocabulary that we are going to learn today, the whole building of lean transformation stands. If we don't understand the complete meaning of the vocabulary that we are going to discuss today, probably it is going to be very difficult for anyone to understand and thereby create a lean transformation model. So all of us are ready? What is the symbol for us? Show me a thumbs up. Wonderful. So let us remain on camera. Let us remain very interactive. Let us try and bring in those examples that you have. And more important than everything else, whenever we are discussing a particular concept, please relate it with some real life situation, some real life case. Maybe not openly discuss that, but you can take a pen and paper and you can understand that, okay, this is the concept that really, this is how this applies in my setup. It can be manufacturing, it can be service, it can be banking, it can be finance, it can be defense, it can be education, it can be hospitality, it can be anything. But try and relate these concepts, how those terms, what these terms mean in your context. That is the best way of remembering those. Okay, so if we are ready, I will first just let you know that we are going to understand value stream mapping. But before we jump into the value stream mapping, I will take you for around on a roller coaster journey for around 1 hour for all these key terms: cycle time, takt time, throughput time, etc. And it is very important that we develop a comprehensive, complete, and correct understanding of all these terminologies. So I will start by discussing and trying to understand, with the help of all of you, the meaning of all these time terms, because these time terms and understanding the crux of these is going to help us that where we are going to focus our improvement initiatives. I will make sure that these things become very simple. And I can guarantee for certain people that they will definitely ensure. I can guarantee for certain people that they will definitely learn these as the best of the professionals. But that guarantee is limited to only a particular set of people. And the first characteristic of that set of people is that they must be on camera. For the rest of people, there is no guarantee. There is just an attempt. But for the people who are on the cameras, there is a guarantee, 100% guarantee. No questions asked. Okay, wonderful. So now, yes, Shweta ma'am.
Sir, actually, I am outside. I'll be reaching home by 20 minutes.
No.
Until then, I will be off camera.
No problem.
No,
Sorry for that. And I'll be listening to the like the training session.
No, having fun actually. So
yeah, wonderful. Thank you. So the point is that the more you are interacting, that more you are deep diving into the core concept, the more you are immersed into this discussion, the more beneficial it is going to be for all of us. So let me start by sharing one of the presentations, which is about cycle time, lead time. So my dear friends, here we are. And so for the next 1 hour or so, this is what we are going to discuss: cycle time, takt time, how to meet the takt time, what do you mean by lead time, throughput time, and what are the ways and mechanisms by which we need to reduce the throughput time and why we want to reduce the throughput time and why we want to reduce the lead time and so on. All that we are going to understand. So in the next few minutes, we are going to have a look at lead time, the throughput time, cycle time, takt time, and how to reduce the throughput time, how to reduce the lead time, why to reduce throughput time, why to reduce lead time, how to meet takt time, and how to establish continuous flow in your organization. My dear friends, so I will try and list out and discuss 10 most used time terms. These are about certain definitions of a particular time, and they are applicable across all the business verticals, be it manufacturing, be it service, be it software development, defense, anything. So the 10 most important time terms. Let us try and start. I will start with very basics, and then we will, you will realize that we are kind of getting into some very relatively complex but highly important terms. So the first is understanding the concept of open time and available time. We are starting with a very simple, and I will need help from some of you. So maybe Rangaraj sir, I will need your support here. Suppose my factory opens at 9 a.m. and I close at 6 p.m. 9 a.m. to 6 p.m. For how many hours I am open? 9 a.m. to 6 p.m.
Hours.
9 hours. 3 hours before 12 and 6 hours after 12. So 9 a.m. to 6 p.m. means my factory is open for 9 hours. So what is the open time, Praveen sir? The open time is 9 hours. Yes? Okay. So Ajay bhai, my factory opens at 9 a.m., closes at 6. Open time is 9 hours. Please note also that I already know and I already declare that I will be closed for half an hour for planned maintenance time. I will not be working. I will not be producing any sellable goods during half an hour, and also be closed half an hour for lunch. So I will also not be producing anything that is worth selling in these half hour plus half hour. So 1 hour I already know. And based on this understanding, I plan everything, because this is what I already know and I have communicated to my whole team. So out of these 9 hours, Ajay bhai, how much is the available time?
8 hours.
8. Everyone clear? Show me thumbs up. Who all are agreeable with this? So although I'm open for 9 hours, since I already know that the planned maintenance time is half an hour, the planned break time is again half an hour, therefore the available time is only 8
hours.
Okay, and can you visualize this, the graphic? Yes, this helps you understand that this is how we understand the distinction between the open time and the available time. Now, out of this available time, unfortunately, most of the times, you will have some time where unplanned breakdowns will happen. Unplanned stoppages will happen. Kind of unavoidable in the real life situation. Therefore, can you see within this green block, which is my available time, some time is already, I know that it will be lost every day. So there was one breakdown here, there was one breakdown here, and the blocks that I have plotted in dark brown are my downtime. Suppose the downtime is, let's say, half an hour. Okay, this is 10 minutes, this is 20 minutes, half an hour is downtime. How much then is the uptime?
7.5 hours.
Wonderful, wonderful, wonderful. So out of the total open time of 9 hours, the available time was 8 hours. And since downtime is half an hour, obviously uptime is 7.5 hours. Wonderful. So this is where the uptime is, this is where the downtime is. And as all of you have confirmed that you understand that the uptime is 7.5 hours. Okay. Now within this uptime also, there will be some time where I know that I will not be producing anything that is worth selling. Some time is lost in setup every day. It is not a downtime. You know that you are going to
Heating, yeah, maybe pre-processing time.
yes. So you set up that, right? Your chillers will come, bring the machinery to a particular temperature. Your
AC.
burners bring the temperature to a particular level. Your air compressors will be operating and creating that particular amount of pressure in the air vessel. So, my dear friend, this yellow box is my set up time. Unavoidable, but present. And also we realize that we will not be able to produce anything which is worth selling in this time also. And these blue blocks, my dear friends, are change over times. Please realize that all the lean practitioners believe and agree that this setup time as well as this changeover time, although non-productive, is part of the up time. Show me a thumbs up who are now realize that, okay, this is what the definition is, right? So for quite some time, there was a debate. Certain practitioners said that, okay, this changeover time and setup time shall be considered as a downtime, but ultimately a consensus kind of emerged that although they are non-productive, but they are within the uptime. Angaraja sir?
Yes, sir.
Yes, sir. Shweta ma'am, show me a thumbs up if that is clear to you. So now we have understood 4 distinct definitions about open time, available time, uptime, downtime, setup time, and change over time. This is the visual that is helping us. So what is the open time? The official work hours, including the break time and the plant maintenance time. What is available time? It's the open time, excluding the break time and the plant maintenance time. Thangaraja sir, can you help us, all of us, read out these 2 definitions? What is open time? What is the available time?
Time, the official working hours, including break time and planned maintenance time. Available time, it's the open time, excluding break time and planned maintenance time.
Yes, and please continue with the downtime.
Downtime, the period of time in which a process is not functional due to unplanned events.
Unplanned event. Yes, please emphasize on the unplanned event. We do not plan these. Please continue, sir.
Downtime includes machine breakdown, unplanned maintenance, waiting for material, waiting for operator, etc. Please note that setup time and changeover time are not considered as downtime, although they are non-value adding.
Yeah, show me thumbs up who all are agreeable with this. This is how the definition has been set up. Now, uptime, the time during which the process is ready to perform its intended function. It is opposite of downtime, and therefore, by definition, it includes setup time and changeover time since they are considered as value enabling activities. Uptime obviously is equal to available time minus the downtime. Now, what is the setup time? The time required to prepare a process to be ready to function or accept a job. Setup time is usually needed once a day at the start of the shift. Correct? For example, starting the operating ovens, setting up the chillers and air compressors, etc. Typically happens only once in a day. What is the changeover time? And this is something very, very important. I would need help from Ajay Bhai to help us explain the definition of changeover time.
So changeover time basically is when we are changing the SKU or changing the parts, the total
Very
machine
correct.
setup is there.
Very correct.
So that we can produce the different set of product.
Next,
If
different
it is
set of
alternate,
product when you're moving
yes.
from one SKU to another SKU. I would like you to read out the definition because this has a very important message here.
Yeah, sure, sir. The time required to prepare a process to change product.
Yeah.
Typically, time duration from producing the last good piece of the last product run to producing the first good piece to next production run.
Yes, please stop here. Typically, the time duration from producing the last good piece of the previous production run to producing the first good piece of the next production run. Shweta ma'am, please listen to my emphasize very with a 100% attention. First good piece of the next production run. Maybe you are, when you are changing, you are producing something, you stop at one particular point in time, say at 40 minutes past 10. Then you set up the machinery and all. Machine is again ready to produce 50 past 10. But the first piece is not good enough, right? Second piece is also not good enough. Third piece is also not good enough. You set the tools, you tweak the settings. Then the fourth piece is good enough to be sold, right? So the first good piece of the next production run, you ramp up when you are adjusting the machine setting, is also your part of your lost time to be considered within the setup time. Is that clear to all of you? Please show me a thumbs up. And I would like Praveen sir to read this out with the necessary emphasis on this fact that the last good piece of the previous and the first good piece. Praveen sir, over to you.
Yeah. Changeover time and setup time. Changeover time, the time required to prepare a process to change product. Typically, time duration from producing the last good piece of the last product run to producing the first good piece of the next product run. Examples include exchange of dies, cleaning of storage bins, machines reconfiguration, etc.
Yes, very correct. So what I want to emphasize, that whenever you change a setup, at times it may happen the first few pieces will not be good enough to be sold, right? And the time, obviously, they will consume. But the emphasis is on the first good piece of the next production.
Next.
So that time lost in machine readjustment, reconfiguration, tweaking of the machine settings, all this is to be considered as part of the lost time, that is part of the setup time, right? And all these are non-productive. Setup is non-productive, changeover is non-productive. Nonetheless, they will definitely happen. So realizing the fact that they are a mandatory evil, we would like to reduce the time that we consume in setup, and we would like to reduce the time in changeover. And therefore, there is a very specific methodology which is known as SMED methodology, single minute exchange of time, which explicitly focuses on how to reduce the setup time. Yes. Now, so we have understood what is changeover time, what is setup time. Now, it is the time to understand that a completely new concept, which maybe some of you are aware, some of you are not, which is about the lead time and the throughput time. What is a lead time? Lead time is the time lapsed between the moment in time when a customer places an order and when the item or service is delivered to the customer. That is what the lead time is. Okay. So suppose you go to, for example, McDonald's. Okay. You place an order, one large fries at 8 p.m. and the order is served to you at 8:20 p.m. What is the throughput time from 8 p.m. to 8:20 p.m.? Angaraja sir, 20 minutes. Applies to everywhere. You request for a checkbook at a bank on 7th of April, and the checkbook is delivered to you on, let's say, 10th of April. 3 days. What is the lead time? 3 days. Yes or no? So the point is that the time consumed between these two events. What are these two events? Order placed by the customer and item delivered to the customer. Delivered to the customer. This is to be considered, this is to be known as the lead time. And what is the throughput time? The total time interval between start of processing operations and completion of processing operations. And this time will consist of processing time and move time and wait time and inspection time. And I'm going to show you a visual by which this will become very, very simple to visualize. This, my dear friends, on your screen is a visual for lead time. Very clear? The time lapsed, the time consumed between these two events, order placed by the customer and order delivered to the customer. And this The next slide is talking of the throughput time. This is where your manager has started his manufacturing operations, and this is where your manager has handed over to you the manufactured product. Some time is lost between here. Okay, I will take one example. Suppose Ajay sir is the general manager operations and I am the factory manager. Ajay sir, are we ready to play this game? Okay.
Yes,
So
yes.
there is a customer who places an order on you, on your factory. You are the factory owner on 1st of January, and you are supposed to deliver on 30th of March. 90 days. From 1st of January to 30th of March. This is what customer is considered. Customer is concerned only about this. He has placed an order to Ajay, factory owner, on 1st of January, and the order is delivered to him on 31st of March. The time lapse is 90 days. For the customer, lead time is 90 days. Okay. Now I am your factory manager. You have received your order on 1st of January, but some time is lapsed for order processing, for raw material planning, raw material ordering from the supplier, raw material incoming, which is the lead time of my supplier, then raw material inspection, and maybe my machines were not ready till 15th of January. So this is where I was de facto able to process your order. So I will say, Ajay bhai, I am answerable only from this 15th of January, when the processing starts. All that time that is consumed in raw material planning, procurement, RM inspection, I am not responsible for that. I am your factory manager only. And this is the point. On 15th of March, I gave you the product. Now, whatever time you have taken or the other departments have taken in dispatch and transportation and delivery to the customer are again beyond the scope of the factory manager. So, Ajay bhai, from the perspective of the customer, the lead time is from 1st of January to 31st of March. From the perspective of the factory manager, the processing time is from 15th of January to 15th of March. Yes or no? And therefore, this is called the throughput time, because this is the time that those particular raw material have spent in your manufacturing pipeline. They entered into your manufacturing pipeline here, and they moved in your manufacturing pipeline, through your manufacturing pipeline like this, and they came out of your manufacturing pipeline here. Therefore, your manufacturing manager, your plant manager, that is Mr. Vivek Kumar, which is me, incidentally, in this role play, will say, sir, my throughput time is 2 months. And you will have to agree, because this has some logic. This has some rationale. So do we understand and do we agree now that the throughput time is within the lead time? Fact number one. Fact number two, these two events are inescapable, inevitable. They will happen. Both these, the pre-production activities and the post-production activities, they will happen, but they are beyond the control of your factory manager, Mr. Vivek Kumar. And therefore, Mr. Vivek Kumar will say, sir, this is my throughput time. In other words, this is time that raw material has taken to travel through your manufacturing pipeline. Please also realize that the biggest part of this lead time is coming from the throughput time. Fact number one. Show me a thumbs up. Yes or no? Show me a thumbs up. Natarajan sir, show me a thumbs up. So the biggest part of this lead time is coming from the throughput time. Fact number one. Fact number two is whatever is happening here is directly under your control or slightly off control. Slightly off control. Slightly off control. This also, the transportation, etc., 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 is also slightly off control. What is highly under your control is your throughput time. भैया किसको बोल सकते हो? सप्लायर को कुछ बोलो पाओगे? नहीं बोल पाओगे. ट्रांसपोर्टर को कुछ बोल पाओगे? नहीं बोल पाओगे. किसको मचकाओगे? किसको डांटोगे? अपने फैक्ट्री मैनेजर को, यानी कि मिस्टर विवेक कुमार जी को आप. द पॉइंट इज Jokes apart, the point is that number one, throughput time is the most consequential part of your lead time. And number two, throughput time is directly under your control. We can try and attempt and successfully reduce the throughput time. Okay, and if that happens, this is how the situation changes. This is the situation which is before improvement. What we have reduced, this is the lead time, this is throughput time. What we have reduced the throughput time. These yellow blocks remaining the same, but the net impact is that the lead time is significantly reduced. So if you want to reduce the lead time, and why would you like to reduce the lead time? I will come to that in a couple of minutes. If you want to reduce the lead time, the best strategy is to reduce the throughput time. Show me a thumbs up if all of us are agreeable with that. Now, this brings us to the question that why would you like to reduce the lead time? For that, I will ask a question to Natarajan sir. Natarajan sir, you want to purchase a book. Yesterday, I told you I'm coming up a book and the name is going to be Navigating to Success. And when that, let's say after 3 months, that book is available on both Amazon and Flipkart for the same price, you go and check at Amazon, it says it will be delivered in 2 days. You go to Amazon, it says it will be delivered in 3 days. You go to Flipkart, it says it will be delivered in 4 days. Which service provider are we going to choose?
Whichever is earlier only.
Yes, which is delivering you earlier. In other words, for the service provider, which is having smaller lead time. Therefore, my dear friends, lead time is in today's day and time the make and break feature of a business. Only those businesses are going to succeed which have smaller lead time. Because typically the cost, the price is kind of dictated by the market. So that will be more or less the same. The quality is kind of dictated by the customer, very well documented, very well defined. So that is exactly what they will expect. The only distinguishing factor between highly successful companies and the companies who are struggling is between the lead times they have. And therefore, do you realize, and I am going to give you an example, the most successful startup concepts in the India in the past 3 years are your quick commerce people, right? People who are delivering in 10 minutes. There is a lot of debate also that it is inhuman and all. But yes, your Zepto, your Blinkit, your quick commerce, because the lead time is extremely. So the just an offshoot of this, when we talk of lean, we say the motto and the definition of a successful lean transformation is highest quality, lowest cost, shortest lead time. This is how Toyota people defined 3 characteristic features: highest quality, lowest cost, and shortest lead time. Realize that those fellows realized this fact in 1940s, 1950s, early 1950s. And therefore, when we create that house of TPS, we say the objective is to achieve these. So lead time reduction is something very, very important. And we have now realized that lead time can be reduced by reducing the throughput time. And how are we going to reduce the throughput time? We are going to learn. But please confirm that by now you are very clear about the definitions of the available open time, available time, uptime, downtime, changeover time, setup time, lead time, and throughput time. Show me a thumbs up if all these 8 definitions are clear to all of us. Now, how to measure the throughput time? As I told you, throughput time is the time of a journey of one particular piece through your site, through your manufacturing pipeline. So whenever, and that is exactly what we are going to do today in next 1 hour, we are going to measure the time taken by one particular piece from start of the pipeline to end of the pipeline. I want all of you to please take a pen and paper and write this down. The throughput time, how do we measure the throughput time? We measure the throughput time by measuring the time taken by one particular piece from start to end. I will share this in a chat box, and I want all of you also to have a look at that. So from the current slide, I am now coming to the chat box, and I am kind of documenting. I am documenting how to. Now let me come to the chat box. Here it is. And yes, so please have a look at your chat box. How to measure the throughput time. Throughput time is the time taken by one particular piece from start to end. Is that clear to all of us? Natarajan sir? Can you read this out? Read this slide. How to measure the throughput time?
Understanding throughput time. How to measure the throughput time? Throughput time is time taken by one particular piece from start to end.
Yes, very critical to remember this, because now things are going to be a little confusing from here onwards. But if you are careful enough and you remember this, the throughput time is the time taken by one particular piece from the start of the manufacturing pipeline to the end of the manufacturing pipeline. And do not be limited to manufacturing only. I'm just, since this is easier to visualize, I am talking of in this term. So I will be taking example of manufacturing because there it is easier to visualize. So throughput time is the time taken by one particular piece from start of the manufacturing pipeline to the end of the manufacturing pipeline. Now, so in the throughput time, what are the components within the throughput time? It will spend that one particular. Now think of one particular piece. It is started moving from one end of the production pipeline. So sometime this piece will undergo while it is being processed upon at machine number 1. Yes. Then it will wait in that bin between machine number 1 and machine number 2. Then again, it will take some time to move from bin to the machine number 2. Sometime then it will spend on machine number 2 and so on. And finally, sometime it will be spending while it is getting inspected. So typically these 4 components, processing time, wait time, move time, inspection time, the fellow will undergo. Now that chapter is closed. That chapter is closed. Now opening another chapter, very different chapter, very different. It is cycle time. And until unless you give 100% attention, there is a big possibility that you will be, anybody can get confused between throughput time and cycle time. These are two completely different things. Throughput time, everyone is clear? Time taken by one particular piece from moving from one end of the pipeline to the last end of the pipeline. So that chapter is now closed. Let me close that chapter. This is how that chapter is closed. Okay. Now opening another chapter. Cycle time. Cycle time is the time required by one particular process to contribute producing one piece of the product. It is the characteristic of the process stage. Cycle time describes your process's rate of output. For example, if the rate of output is 60 pieces per hour, Praveen sir, Thangaraja sir, Ajay sir, Natarajan sir, if I tell you that this particular machine, this particular, let's say, drilling machine or turning machine or stamping machine or cutting machine produces 60 pieces per hour. This is the rate of output. In other words, I can say that the cycle time is 1 minute per piece.
Yes.
Right? So these two are related. Rate of output can be expressed in terms of the cycle time. Okay, so now let us play a quiz, Praveen sir. If I tell you that for machine number 1, the rate of output is 60 pieces per hour, what is its cycle time?
1 minute
1 minute per piece. The full
per piece.
Yeah,
Yes,
1 minute per
piece.
piece. Let us stick to the full. Yeah. Now, if I tell you, Praveen sir, for the machine 2, the rate of output is 30 pieces per hour. What is the cycle time?
30 seconds per piece.
No. Wrong.
2 minutes.
It is 30 pieces per hour. So it is taking
Pieces
2
per hour.
minutes per hour.
2 minutes.
30 minutes per hour is 2 minutes per piece.
2 minutes per piece, right?
Per piece.
So if I tell you that, okay, there is machine 3, which is producing 120 pieces per hour. What is the cycle time? Half a minute per piece. Yes or no? So we can definitely convert in very simple terms, said what is the cycle time. So the cycle time, remember, is the time after which your machine throws out one piece. Remember this. Cycle time is the time after which your machine throws out one piece. So for this particular example, where the rate of output is 60 pieces per hour, cycle time is 1 minute per piece. So this machine is throwing out one piece every 1 minute.
That is called speed, basically.
Yes. So since we are talking in terms of time, so we will say that is a cycle time. Okay, so cycle time is the characteristic of every machine. Every machine can have, rather will have, a different cycle time. Yes, is that clear? So when we are talking of cycle time, it will be primarily a characteristic of a particular machine. And various machines in your pipeline, although they are in a sequence, may have a different cycle time of their own. Now the overall cycle time, we'll come to that. Okay, there will be overall cycle time also, but we will come to that. Right now, just remember that every machine, every process stage will have its own characteristic cycle time, that after so many minutes or after so many seconds, it throws out a piece. Okay, so now the distinction is clear between the throughput time. For a throughput time, you look at one particular piece and map its journey.
Yeah, it may be more than cycle time.
It will be very different.
Yeah, different.
Obviously,
Totally
more than also, and it is a completely different concept. Let's not confuse between these two. These are two completely distinct concepts. So when you are talking of throughput time, you think of one particular piece and map its journey throughout the pipeline. You travel with this particular piece, and then you say that, okay, this much time it has taken for moving from start of the pipeline to the end of the pipeline. That is what the throughput time is. And a completely different concept is cycle time. For calculating a cycle time, you do not look at one particular piece, you look at one particular machine. And see that after how much time this machine throws out one piece.
Sir, is it possible to...
It will be very simple. Just remember this. We will have a lot of graphics here and we will have a lot of discussions on that. Right now, I just want you people to realize that these are two completely different things. Yeah. Okay. Now, what is the takt time? Takt time is the third concept. Third concept is it's dependent on the demand. It is the rate, it is the speed at which your customer wants you to produce. Whether or not you can meet your demand or not is a separate question. But takt time can be completely determined even without knowing anything about your setup, about your machine, because this is completely defined by what the customer demands. Okay, so these are the things. Now, let us try and visualize, and it will become very simple for all of you. Please come on camera. This is something very interesting and can be quite confusing also if you are not 100% immersed into the discussions. So this is how typically a process happens. There is operation 1. This is my manufacturing pipeline. Ajay bhai?
Yes, sir.
Praveen bhai, this is my Ramachandran sir. Suvarna sir, this is my manufacturing pipeline, and this is how operations typically happen. There is operation 1, then goods will be waiting in the WIP bin, then they will be moved to the operation 2, then they will be waiting in the next WIP bin, then they will be moved to the operation 3, and then they will be moved to, they'll be waiting in the WIP bin for inspection, and there will be inspection happening. This is how a typical manufacturing setup typically is. I request all of you to please come on camera. This is something very, very interesting. Yes. Okay, perfect. So I can see a lot of people now. Wonderful. Now, let us assume, for the sake of discussion, for this operation 1, it makes 320 pieces in 480 minutes. Why I have taken 480 minutes? Typically 8-hour shift.
Right.
Every 8-hour shift has got 480 minutes. Okay. So this operation 1 is making 320 pieces in 480 minutes. For the sake of simplicity, I have taken operation 2 is also making 320 pieces in 480 minutes. Now, who can calculate cycle time for me for machine number 1? Naresh Reddy, sir. 320 pieces. So 1.5 minutes it is taking.
40
Yes, sir.
PPM होगा.
1.5 minutes it is taking for throwing out one
Yes,
piece.
1.5
For
minutes.
every piece it is taking 1.5 minutes. Yes or no?
Correct, sir.
This machine is taking 1.5 minutes. That is 90 seconds for every piece. So 90 seconds per piece. Everyone show me a thumbs up. Rather simple. Rather simple. So cycle time here is 1.5 minutes, or you can say, let us convert that into seconds. So 90 seconds. For the sake of simplicity, here also 90 seconds. Now, here also 90 seconds. For the sake of simplicity, we'll go to the complex situations later. Right now, this line is perfectly balanced. All my machines are throwing out one piece every 1.5 minute. This machine is throwing out one piece every 1.5 minute. This machine is also throwing out one piece every 1.5 minute. This machine is also throwing out one piece every 1.5 minute. Now, let us assume that there is a WIP bin. I have designed my process in such a manner. This WIP bin is for 50 pieces. Now, let us play a small game. Lisa ma'am is there. Lisa ma'am, and it is very, very simple, child's play. So, if this machine throws out one piece every 1.5 minutes, how much time it will take to fill this bucket of 50 pieces? 50 multiplied by 1.5?
450.
Yes?
75.
70. 70. Yes, very correct. Very simple. Child's play. So how much time it will take to fill this bin? And I move this bin only when this bin is filled, completely filled. Okay. So one piece, every piece is spending 1.5 minutes here, and it is spending 75 minutes here in this bin. Yes, and we can convert how many seconds are there. Then it takes 20 seconds to move there. I can have another situation also. Maybe I can decide that instead of 50 pieces, I will have a bin for 100 pieces. I can decide. Possible?
Yeah.
Possible. But I have decided that I will have this bin for 50 pieces only. So this is the set. This is how the setup is. So the cycle time here is 1.5 minutes. Because the rate of output is 320 pieces in 8-hour shift for 80 minutes. Cycle time for this operation 1 is 1.5 minutes. That is 90 seconds. That is every 90 seconds, the operation produces one piece. Please show me a thumbs up if all of us are following this simple, very simple concept. Okay. Now, WIP bin is for 50 pieces. WIP bin can be for 100 pieces also, whatever you decide. I am intentionally showing you to demonstrate that how these WIP bin sizes affect, what they affect, what they do not affect. But for the moment in time, just know that I can decide I can have a WIP bin for 50 pieces, or I can decide I will have a WIP bin for 100 pieces or 200 pieces or 20 pieces, whatever. For the sake of simplicity, for this example, cycle time for operation 2 is also 1.5 minutes, and so on. So this is how one particular piece is going to spend its time. So, Praveen sir, let's calculate the throughput time for one particular piece. What we are going to calculate? throughput.
Throughput time.
Natarajan sir, what we are going to calculate? Throughput time. Right, sir, what we are going to calculate? Throughput time. What is throughput time? Time it takes for one particular piece to travel from one end of the pipeline to the last end of the pipeline. So this particular piece will spend how much time here? 1.5 minutes, 90 seconds. Yes.
Yes.
How much time it will spend here? 75 minutes, which is converted, which I convert. Please calculate. Simple. It is 4,500 seconds. So 90 seconds it will spend here. 4,500 seconds it will spend here. 20 seconds it will spend here. Again 90 seconds here. 4,500 seconds here. 20 seconds here. And so on. Lisa ma'am, can you help me calculate?
Yes,
How
sir.
to reach to this? 4,500, 75 minutes multiplied by 60 is 4,500.
Focus.
So if I want to calculate the throughput time for one particular piece, so 90 plus 4,500 plus 20 plus,
5,420.
and this is happening thrice, so totally 13,830 seconds,
3.8.
which is 3.84 hours. One piece will take 3.84 hours for moving from this point to the output point of my production pipeline. Show me a thumbs up if this concept is understood. Yes, Ramchandran sir? Shall I repeat? Anyone? Anyone? Very simple. So this, my dear friends, is how I calculate the throughput time. Now, please tell me, if I change my bin size from 50 pieces, I change it to, let us say, 100 pieces. Then this 4,500 second will be doubled. And therefore, you know that throughput time will significantly increase. Correct? Is that clear to all of us?
Clear.
Significantly increase. So the bin size significantly affects your throughput time. Is that clear to all of us?
Right.
Let me show you that. I will stop share this. I will share one Excel sheet. I will show you the calculations. I will share an Excel sheet. Let me share.
If we are changing the bin size, the overall time will be 7 hours, 7.59 hours.
Yes, let us calculate. Let us calculate. Earlier, what it was? Earlier it was
3.84.
Yes. First, let's delete all this. Let's calculate. We all remember. So on the first machine, it was spending 90 seconds. Yes. Then here it was spending. So since it was 50 pieces multiplied by 1.5, multiplied by 60. So 4,500. Yes. Then it was spending 20. Right. And so this was for one block.
We have to copy paste it for thrice. It is the same thing, right?
Yeah. Or otherwise, I will multiply it by 3.
Yes.
Same thing.
We
Yes.
can do that.
So therefore, it came out to be 13,830 seconds. And let me convert this into hours. And then let me convert this into seconds. Sorry, first let me convert into minutes, then let me convert into hours. So 3.84 hours. That is exactly what we saw there. Now, if instead of this 50 pieces bin, I have a bin of, instead of this 50 pieces bin, I have a bin of 100 pieces. What will happen? It is gone to 7.59 hours. Can all of you see this? So your bin size is significantly affecting your throughput time. And also, instead of, let's say, let me come back to this. I was sharing this. Okay. And instead of, let's say, increasing it to 100 pieces, I reduce it to, let's say, 10 pieces. What happens?
Increases. Reduces.
Significantly reduced to 0.84 hours. Is that clear to all of us? So we all now realize that your bin size significantly affects your throughput time. All of us, please show me a thumbs up. Is that concept is clear? Okay. And also please note that when I am changing my bin size from 50 pieces to 100 pieces to 10 pieces, whatever, is this having any impact on the cycle time? No.
No.
Therefore, let us show me a thumbs up. I will stop sharing. I want all of you to please come on cameras for a minute, just for a minute, all of you, so that we can, I can confirm that all of you now realize that your bin size is significantly, your bin size is where is this? Your bin size is significantly affecting the throughput time, but the bin size is not at all affecting your cycle. Show me a thumbs up if both these concepts are clear to you, right? So who will repeat this? I will ask this question and I want to hear from, let's say, okay, I cannot read out the names correctly because I am not so much used to. So maybe Naresh Reddy sir. So please tell me, if I change the bin size, will it impact the throughput time?
No, it will not impact the throughput time.
It
Bin
will impact.
size,
No. Bin size will
bin
impact.
size will impact the overall production
Impact
time.
the
So
throughput
obviously
time.
cycle time will be getting impacted.
No.
No.
Bin size will be impacting only the throughput time,
Yes.
not the cycle time.
The cycle time.
Not the cycle time. When I come back to my slide, you will realize that. Yes, Suvarna sir.
So there are certain cases where one piece flow will be there, where the bin size will be zero.
Yes, exactly. And that is exactly why people realize that we want to achieve single piece flow, because the smallest possible bin size is one piece. So the logic is this: as you
It is called
reduce,
conveyor system.
yes, as you reduce the bin size, throughput time gets reduced. And you want to reduce the throughput time because you want to reduce the lead time. Okay, I will build my argument like this. You want to reduce the lead time, yes or no? Show me thumbs up. You want to reduce the lead time? Yes. Therefore, you want to reduce the throughput time? Yes. You realize that throughput time can be significantly reduced by reducing the bin size.
Bin size.
Therefore, let's reduce the bin size to the minimum possible. Yes.
Yeah.
What is the minimum possible bin size? 1. Therefore, shall we go for single piece flow? Yes. That is the concept that tells us why we are going for the one piece flow. Somebody wants to ask something? No? Okay, perfect. So I will come back to
Yes,
my...
sir, I want to ask one question.
Yeah, please.
What
Please
about what about this turnaround time TAT?
we will come to that. We'll come to that.
Okay, sure, thank you.
Yeah,
Bin
we'll
size can
definitely
be
come to
zero
that.
also, sir.
Pardon?
Bin size can be zero also.
Theoretically, yes, but practically, no. Okay, so now coming back to my core presentation here. So my dear friends, now all of us are agreeable that we want to reduce the bin size for the sake of reducing the throughput time. Please show me a thumbs up. And please also note that this bin size has got no impact, none at all, on the cycle time.
Correct.
Is that clear? And there are other ways, other strategies, other ideas that we can use to reduce the cycle time. We will definitely want to increase the production. We will definitely want to reduce the cycle time and all. But that is a different story altogether. Okay. Now, coming to this. Now, let me see how much time is actually the piece is getting worked upon, and all the other time is a kind of, it is resting or idling or waste for this particular piece. This particular piece is being worked upon only for these 90 seconds. Only this 90 seconds. Yes, not here. It is just waiting here also. Nothing is happening to it. So 90 seconds here, 90 seconds here, and 90 seconds here. These 90 seconds thrice that is exactly what your processing is happening. Fact number 1. So processing time is 90 seconds plus 90 seconds plus 90 seconds, 270 seconds only. Also, third concept, if this machine is throwing out when the pipeline is full, now assume the pipeline is full. After 2 hours, let's say the pipeline is full. This machine is throwing out one piece every 1.5 minutes. This machine is also throwing out, this bin is also throwing out one piece every 1.5 minutes. Yes, this machine is also throwing out one piece every 1.5 minutes. This bin is also throwing out one piece every 1.5 minutes. Your last bin is also throwing out one piece every 1.5 minutes. So if you look at the output side of your production pipeline is throwing out one piece every 1.5 minutes. Yes, once the pipeline is filled, it will take some time to get filled. You start your factory at 9 a.m., setup time, whatever, but let's say after 2 hours, the pipeline is full. And typically it will remain full because when you go home at the end of the day, you do not empty the pipeline. Yes. So typically pipelines are generally full. So if I ask you that if the rate of output, that is the cycle time for this operation 1 is 90 seconds per piece, 90 seconds per piece, 90 seconds per piece, 90 seconds per piece. What is the cycle time of your whole setup, your whole production setup? Again, 1.5 minutes, that is 90 seconds per piece. Yes or no? 90 seconds per piece. Now let us complicate a situation a little. Suppose this machine is taking 2 minutes per piece. This machine is taking 2 minutes per piece. So this machine is making 1.5, this machine is taking only 1.5 minutes, but this machine is taking 2 minutes per piece, and therefore its output, this machine will be starving. It can consume and produce one piece every 1.5 minutes, but it will not get. So the overall cycle time of your whole setup is dictated by the highest cycle time of your various processes. So we will have a couple of examples around that, and then this concepts will again become very, very simple. Okay. So till now, everyone, just show me a thumbs up. Everything is clear? Yes. No complications? Okay. So let us take another simple example. Here in this particular operation, the output is 320 pieces in 8-hour shift, that is 480 minutes. That means cycle time for this operation 1 is 1.5 minutes, that is 90 seconds. That is, for every 90 seconds, the operation produces one piece. Everyone clear till this? Now, let me explain. I looked at this machine, I studied this, and I observed that this machine was productive only for 320 minutes, while the machine was stopped for breakdown for 53 minutes, 53 minutes for changeover, 53 minutes for setting up. So actually this machine was working only for 320 minutes. And if I think about it, so for every minute it was working, it was giving me one piece. Unfortunately, it was not working because of the breakdown, because of changeover, because of the setup, that time was lost. So if I want to increase the output from this machine, what shall I do? Very logical. Shall I try and eliminate the changeovers? Shall I try and eliminate the breakdowns? Right? So suppose if I am able to make sure that this machine is having no breakdowns, no changeovers, then the output will be increased. Yes. Then maybe For every 480 minutes, it will be giving me 480 pieces. Yes, and therefore cycle time will be improved. So for improving the cycle time, when I say improving the cycle time means reducing the cycle time. Okay, so for improving the cycle time from 1.5 minutes to 1 minute, what I shall be attempting? Shall I be attempting and looking at the bin size? No, bin size has got nothing to do with it. What has got to do with this is the breakdown time, the changeover time, the setup time. We will have a look at this. So very simple. Look at this. Cycle time for this operation in this particular case is how much? This machine produced 320 pieces. Machine was productive, Ajay sir, for 320 minutes. Machine was stopped for 53 minutes. Machine was for the breakdown. Machine was stopped for 53 minutes for changeover. Machine was stopped for 54 minutes. That is these many for the setting up. Okay. And therefore, the meaning is the machining time is only 320 minutes. In this machining time, the machine produced 320 pieces. So as far as the machining processing time is concerned, it is taking only 60 seconds per piece. Ajay sir, Praveen sir,
Sir.
Suvarna, Naresh sir, Natarajan sir. Yes, machine processing time is 60 pieces per second. And for every piece, 10 seconds, let's say this is for the sake of simplicity, 3,200 pieces. Right?
Sir. Sir, எங்க இருக்கீங்க?
So,
எங்க இருக்கீங்க?
10 seconds per piece, it is.
Sir, எங்க இருக்கீங்க? Sir, எங்க இருக்கீங்க? கேக்குதா?
10 pieces, 10 seconds per piece are lost in breakdown, 10 seconds
Sir,
per piece are lost in changeover pieces, changeover, and 10 seconds per piece are lost in this. Suppose if I'm somehow able to eliminate.
थोड़ा confusion हो गया.
जी बताइए.
You mean to say that 320 pieces are produced, including these breakdown and these 53, 54.
Yes.
Oh,
In I mapped it, I monitored it for whole shift.
Oh.
In the whole shift, the output was 320 pieces.
Oh.
Then I realized that out of this, the whole shift, the machine was kind of under breakdown for around 1 hour, for 1 hour for this man and for that. So typically, this is what is happening.
Yeah, value added time.
Yes. And this is a real life situation. Every day it will happen. So every day it will happen. So whenever you want to calculate the cycle time, you do not take a stopwatch and calculate a cycle time. Please note, very, very interestingly. You do not take a stopwatch to calculate the cycle time. You take out the output of the whole shift. And then you calculate that in the whole shift, this much output is there. And then you look further deeply into that. And then you realize that the cycle time is high because of the breakdown, because of the setup, because of the changeovers. And therefore,
sir, question is here. For a system either in FMCG, how many shifts output should be checked ideally?
Ideally, you need to monitor for 3 days, 3 shifts, 9 shifts. And then only you will have an average understanding. Because every shift, the same amount of breakdown will not happen. But if you monitor for, let's say, 9 different measurements spread over 3 days or spread over 9 days, if you are working only one shift, then it gives a kind of a representative.
That's it. Thank you.
So how much is the typical changeover time? How much is the typical breakdown time and on? So now we have realized, my dear friends, a very interesting fact. If I want to improve, that is reduce the cycle time, I shall be focusing my efforts on reducing the breakdown time, reducing the changeover time, reducing the setup time. Is that clear? And if I want to reduce my lead time, that is throughput time, I shall be focusing on bin size. Okay.
So it will improve the cycle time also.
Cycle time is getting impacted only because of these things.
Yeah, these
Can
three
you
things.
see? Yes, only these things. No, it is not at all affected by cycle time, is not at all affected by the bin size.
Yeah, I'm not
Cycle
talking bin
time,
size. I'm talking about this operation one. If we
yes.
remove this breakdown, changeover, and setup time, then cycle time will improve, and parallelly, our throughput time will also improve.
It will also be reduced, but very marginally.
Okay.
You will see. You will see very marginally. Because it is 90 plus 4,500 plus something. So you reduce that 90 to 60.
Yes.
Right? You remember that equation?
Right.
Let's come back to this. 90 plus 4,500 plus 20. So suppose you make improvement here. Instead of 90, it is now 60. Yes, but the impact is there, of course, but very small, kind of insignificant on the throughput time, but significant impact on your output. Is that clear? Can we calculate? I will stop sharing here, and I come back to my Excel sheet so that I can explain to Ajay sir. So let's say here, this was my original scenario, 50 pieces bin size, and therefore it was 3.84. Remember that? So now I do not make any changes in this 4,500, bin size remaining the same. Let's improve the cycle time and all. Instead of 60, instead of 90, it is only 60 now. Let us see how much it impacts. Only 3.81. From 3.84, can you see, to 3.81. Very insignificant. So there is no really point in getting happy that there are other ways, other reasons by which, because of which you will become very happy. Because reducing cycle time is also very, very beneficial. Very, very beneficial because your output increases. But it has no impact on in a manner of saying no impact. I can say bringing it down from 3.84 to 3.81 is no impact at all. There are other benefits. Your production, your productivity has gone up 1.5 times. So instead of every day making 320 pieces, you are every day making 480 pieces. Yes. Okay, perfect. So now coming back to my presentation here. So now all of us are realizing that throughput time is a very different feature, important feature, of course, but very different than cycle time. And throughput time gets primarily impacted by the size of bin, and cycle time primarily gets impacted by your breakdown and setup and changeovers. And both these characteristics are important, because if instead of making 320 pieces per day, you are making 480 pieces per day, because you have improved your cycle time, it is something to celebrate. Very, very big achievement. But please realize that it has got no impact on your throughput time. That is a different characteristic altogether, and you want to improve both. So therefore, you will work on reducing the bin size, as well as you will work at reducing your cycle time as well. But please remember, these are two different characteristics. Let us not confuse, and most of the people, even senior people and academicians, at times get confused between these two.
Sir,
So
is
this
there
is
any possibility to the throughput time will be lesser than the cycle time? Any case?
You see, these are two completely distinct characteristics, fact number one. But just for the sake of, let me tell you that whatever you are asking is not possible. Why? Let us come to this. You want to compare the cycle time and the throughput time. Okay. Now, the throughput time, suppose in this slide, I will just okay. Oh, sorry. I will share once again, and I will show you how that happens. Okay. So for your case, let's say for number one, you want to reduce the cycle time and you want to compare. Suppose I eliminate this. Suppose I eliminate this. Okay. And I suppose I eliminate this as well. Okay.
There are only one operation of cycle time. That's all. It is equal to throughput time. As simple as that, right?
No. This particular piece, now remember, this particular piece will spend 90 seconds here.
Correct.
And 90 seconds here. And 90 seconds here. So throughput time in any ways will be 90 seconds plus 90 seconds plus 90 seconds.
Correct. Correct.
While the cycle time for this machine is 90 seconds. This operator will say, sir, my cycle time is 90 seconds.
So if sir,
This
so
operator
question
will
is,
also
so
say,
question is if there is a
I
single
will come to
operation.
your question. I will come to your question. Let's first me clarify this. So this operator, this machine will say my cycle time is 90 seconds. This operator, this machine will also say my cycle time is 90 seconds. This operator, this machine will also say my cycle time is 90 seconds. But one particular piece will have to spend 90 seconds here and 90 seconds here and 90 seconds here. Therefore, the throughput time, which is the time taken by one piece to travel from start to end, is 270 seconds. Therefore, it is just not possible with multiple machines to have cycle time equal to throughput time or throughput time lesser than the cycle time. It is only possible if I eliminate this machine also and I eliminate, there is only one machine.
Exactly. There is only one machine, exactly.
One machine.
They can be equal.
Only one process. Only in that case, even theoretically,
equal to cycle
time will be equal to the throughput time. Is that clear? So please always remember this core concept of throughput time. The throughput time is about the time taken by one piece to travel from one end to another. As you increase more process stages, the cycle time, the throughput time will increase.
Sir, suppose there is a case where machine is taking a processing time 1 minute, right? And in 1 minute, that machine is producing, suppose 5 lakh pieces. Then the cycle time will be lesser than the processing time, is it?
No. You are kind of confused. Let us take your example here itself. This is one operation number one.
Single operation. I'm asking for single operation. If the machine capacity producing 5 lakh unit per minute. So, but processing time is only 1 minute.
No. Processing since no. I will explain. Since it is making 5 lakh pieces per minute.
Yes.
So for one piece, how much time it takes to get processed?
Yeah.
1 divided by 5 lakh.
Correct.
Right? So very small fraction. One piece will spend, let's say, nanosecond.
Right.
That is a cycle time. So the definition of cycle time is the time it takes to throw out one piece. Yes. So every nanosecond, it will be throwing out one piece.
Right, clear.
Right. So remember the time it takes for a machine to throw out one piece. So every nanosecond, it will be throwing out one piece. If it is making 5 lakh pieces in a minute. So if you stick to the core definitions, there will not be any confusion. Okay. So to kind of close this discussion, I would like to reiterate and understand from all of you that do you people now understand that throughput time is a different concept?
Correct.
Which is tracking the journey life of one particular piece from one end to other end. Cycle time is a completely different concept, which is talking of how much time particular process stage or a particular machine takes to throw out one piece. So for this machine, it is throwing out one piece every 90 seconds. This machine is throwing out one piece every 90 seconds and so on. And intentionally, I had taken the most simple cases where all the three machines are having the same cycle time. But situations will be complicated than this. So the situations, let us again see how the situations will be complicated. Suppose this is a situation where this machine is throwing out one piece every 1.5 minutes. And this machine is capable of, listen to me very carefully. This machine is capable of throwing out one piece every 1.2 minutes. But will it be able to? It will not be, because it is getting only after every 1.5 minutes. Yes, so this machine will be starved. Second machine तो क्या होगा, भूखों मर जाएगी. Is that clear? Similarly, this was the case 1. Everyone clear about this? This is case 1. Let us take case 2. This machine is throwing out one piece every 1.2 minutes. But this machine can produce and therefore consume one piece every 1.5 minutes. What will happen? There will be
Surplus.
Surplus.
Build up.
Exactly.
Build up.
So there will be a built up of inventory at this location. So when the cycle times are not balanced, what will happen? Either the machines will be starved or there will be built up inventory. Both these situations are undesirable. Therefore, isn't it a good idea to make sure that the cycle times of every process stage is more or less the same? Simple. Angaraja sir, do you agree with this? So this situation is bad. This situation is bad. Therefore, one clue is that to have a smooth flow in the process, establishing flow, creating flow. This is one of the principles of lean. We must calculate the cycle time of each and every machine and try and find ways by which the cycle times of each and every process stage is more or less the same. Otherwise, flow cannot be there. Do you agree, all of us? Simple. Now, with this, let me check this. So this is a situation where this machine 1.2, simple, 480 minutes, 400 units, 1.2 minutes per piece, 1.5 minutes per piece. Here also, this machine is capable of 1.2 minutes. What is the overall cycle time for my whole setup?
22%.
This machine is dictating. Yes or no? This
Right.
machine is throwing out one piece every 72 seconds, it will throw out. But this fellow will consume and throw out only at every 90 seconds.
90 seconds.
Is capable of. This machine is capable of throwing out and therefore consuming one piece every 72 seconds. But will it be able to do? No, because its supplier is stuck here. So what is the bottleneck here? This machine. Operation 2. So now onwards, when we are doing VSM, that is value stream mapping, how will we identify the bottlenecks? The machine which is having the highest cycle time is the bottleneck. The machine which is having the highest cycle time is the bottleneck. Show me a thumbs up. Very simple concept. Very simple concept. So now we have learned a very simple way, a very practical way of identifying the where is the bottleneck. Calculate the cycle time of each and every machine individually. I told you that the cycle time is a characteristic of each process stage or every machine. Then find out which machine or which process stage is having the highest cycle time. And that is your bottleneck. Then next logical step, you want to balance out at first because you want to have flow. So what is the trick available to improve, that is reduce the cycle time here? Will we succeed if you look at the WIP bins? No, we will not, because cycle time is not impacted by that. We demonstrated that. So how it will be impacted? What impacts this? Breakdown time, changeover time, setup time. So if we look at this, we can improve, that is reduce the cycle time there. Now, this brings me to another interesting concept, which is known as the takt time. Till now, everything okay? Just all of you, please show up for once and please confirm that till now everything is digestible. Simple. Okay, perfect. So now we have understood throughput time, lead time, what impacts throughput time, what is cycle time, what impacts cycle time, why we want to reduce the throughput time, because we want to reduce the lead time. Why we want to improve that and reduce the cycle time? Because we want to increase the output, the rate of output. So instead of 320 pieces, we want to make 480 pieces. That is the impact of cycle time. And how to improve that and reduce the cycle time is by reducing the machine stoppages time. And as I told you, machines get stopped because of the breakdown. Machines get stopped. Now listen to me. I am even deep diving into this. Machines not only stop only because of the breakdowns. I have spent 35 years in industry. Machine stop because of the breakdown. Machine stop because of the non-availability of the raw material. Machines stop because of non-availability of the competent manpower. Machine stopped because of the quality assurance approvals. Machine stopped because there is no electricity. Machines stopped because nobody thought it was important to keep it running. They take it lightly. Machines stop because of various many easy to solve reasons also. Machines stop because was there no drawing provided to the operator and he was waiting for what are the specifications. Machines stop because the measuring equipment was not provided to the operator so that he can make sure that the piece I am turning has been turned to the correct dimension. So, my dear friends, machines do not stop only because of the mechanical or electrical breakdowns. There are various many silly reasons also. So we must make sure that the machines are fed, operators are there, equipment are there, tools are there, drawings are there, specifications are there, work instructions are there, SOPs are there, quality approvals are there. And therefore, in best of the companies, in the most evolved of the companies, there is a concept of end-on light. Hope some of you might have seen those end-on lights. And in now digitalized world, there are digital trackers which keep showing the output of the last 1 hour or last half an hour or last 10 minutes so that you can make sure that whether or not machines are running at the optimum speeds. And all those go into a war room type of a thing. I have myself created a war room for a company which is having 1,000 machines. And it gives me extremely strong control over the output of the machinery. I do not allow the machines to stop because of the silly reasons. Okay, so coming back to the concept that we were discussing here. My dear friends, this is what we were discussing. So throughput time and everything we were discussing here. So now we are clear about the throughput time and those concepts. So coming back to this. Okay. Now the takt time. Takt time is the rate at which the customer wants you to produce. So I want you to calculate one simple calculation. Who will do that? Who will do that calculation for me? Let's say Praveen sir will do that calculation for me.
Yes,
so
sir.
a customer comes to you on, let's say, Monday morning. He is talking to you on Sunday and he says, okay, tomorrow you produce things for me. And by evening tomorrow, 5 p.m., he's talking to you Sunday morning, sir. Praveen, sir, you are the business owner. He is talking to you 10 a.m. in the morning on Sunday. And he's saying that, Praveen, sir, tomorrow I want you to deliver me 480 pieces. And you are running your operations in one shift. You know that. So what is the takt time? I will explicitly give this case study for everyone to think. The customer, that is Mr. Vivek Kumar, is talking to a business owner, Mr. Praveen, 10 a.m. Sunday morning. Sunday is off day for the factory. The factory will open tomorrow. You are working in 8-hour shift. 8 hour is your available time, not the open time. 8 hour is your available time. And I, the customer, tells you that, Praveen sir, I want 480 pieces delivered to me tomorrow 9 p.m. What is the takt time?
8 hours divided by?
Yes, exactly. Very correct. Very correct.
280 pieces.
Yes, so you have got 8 hours, that you have got 480 minutes. He wants 480 pieces. Therefore, the takt time is 1 minute per piece. And do not confuse it from 10 a.m. in the morning of Sunday to 9 p.m. in the evening of Monday. Your available time. So you compare your workable production hours, that is your available time, with the units required. So the customer wants you to produce at a rate that you consume 1 minute per piece. Now, if the cycle time, you know, you have calculated, you have been through to this master class, and you calculated your cycle time of every machine and of your whole process, and you realize that my whole cycle time of overall process is 1.2 minutes. Customer wants takt time is 1 minute.
1 minute.
1 minute per piece. Your cycle time under the present scenario is 1.2 minutes per piece. Will you be able to meet his demand? No, you will not be able to meet his demand. Therefore, for the business owners, it is important to realize that if you want to meet the demand of the customer, the cycle time must be less than the takt time.
Sir, the customer demand is, let's say, here we are saying 480 pieces, but, you know, along with the cycle time in my process, which is, you know, 1.2 minutes, 1 minute and 20 seconds. There is also throughput time, because there is a, you know, if there are multiple machines, I'll have to consider the throughput machine also.
You are very correct, but right now, you are very correct. Right now, let's focus on this thing only. Then I will come to throughput time.
Agree.
Then I will come to throughput time and all.
Agree.
Right now, let me first make sure that your present capacity of production in one day is not meeting the customer demand. In other words, what you compare your cycle time and you compare the takt time, and you know whether or not my capacity is. And now to answer your question, at times throughput time can be significantly important in a business, at times it might not be. Suppose you are in a business of producing, let's say, nuts and bolts. And you are in any ways making M20 bolts in any case. Your pipeline is full with M20 bolts, whole pipeline. And there are various machines. There is cutting, there is turning, there is stamping, there is threading, everything is there. But since your pipeline is full with M20 bolts, and I'm also asking for M20 bolts. So from tomorrow in the morning, whatever you produce, you start your machinery at 9 a.m. and 1.5 minutes past 9 a.m. there will be one bolt coming out of your pipeline because the pipeline is full. Yes.
No, but that will not be dependent on the units, that is the unit demand that the customer has actually put.
Yes, exactly. Right now, what I'm trying to explain, your question about the throughput time. So, in certain cases, throughput time might be an insignificant fact. So, just assume this. So, you are in any ways making M20 bolts. Your pipeline is full with M20 bolts. Maybe there are 10 machines in a sequence, but all that is irrelevant, because in any case, tomorrow when you go and start your machines at 9 a.m., 1.5 minutes past 9 a.m., you will have your first M20 volt. But
my question is, see, when you're talking about takt time, you are neither bringing in the cycle time into this when you are mentioning working production hours and the total number of units in demand from the customer.
So the takt time
neither
is
we're
to be
talking about the
compared.
cycle time, nor we are talking about the throughput time. So
Exactly. The takt time has got relevance with respect to cycle time. So we need to. It has got relevance only with respect to cycle time, not with relevance to, because lead time is something very, very different. Throughput time is something very, very different. So takt time has got relevance only with reference to the cycle time. Fact number one. Fact number two, your cycle time shall be less than the takt time. Everyone clear about this?
Yeah.
And also
Yes,
very
absolutely.
interestingly and very importantly, the cycle times of all your various different processes shall be more or less the same to make sure that there is flow. Yes? Okay. So this is why we always compare takt time with the cycle time. They are to be matched in the sense there your cycle time shall be less than the takt time. And therefore, to the last slide of this discussion, cycle time is what we can do and takt time is what the customer demands. And customer will demand whatever he will. And therefore, we can try and improve our cycle time. Okay. So, who will read this out? Maybe Praveen sir?
Yes, sir. Understanding cycle time and takt time. Meeting takt time. Takt time is dependent on customer demand.
Correct.
Takt time has nothing to do with how fast equipment operates or how fast workers are able to move. It is the blunt reality of how fast production must be to meet the deadlines. Takt time is number of units in an order divided by the amount of workable production hours. It is about what the customer expects from us.
Yes, exactly. So in this case, customer demand is 480 minutes, 480 pieces. Takt time is 1 minute per piece.
1 minute per piece.
But what we can do presently is 480 minutes, 320 pieces. Takt time is 1.5 minutes per piece. Therefore, we will not be able to meet the customer demand. Therefore, we must try and strive and work towards reducing the takt time. What is the area where we will be focusing? Breakdown time, changeover time, setup time, machine stoppages time. And by that, we will be reducing our cycle time so that we are then able to meet the. Therefore, the crux of the whole discussion, starting from all that very simple concept, factory opens at 9 a.m., close at 6 p.m. Now we have reached to a very complex and very important conclusion that cycle time should be less than or equal to the takt time. Okay, so that is all from this side. Now come to VSM thing. Because for understanding the VSM, that is value stream mapping, all this basic understanding of this vocabulary is going to help us a lot. So if you have understood all this, then the concept will become very, very simple to understand. So are we ready to jump to the value stream mapping thing? Okay, perfect. Let us. Okay. So the value stream mapping. Typically, what happens when we talk of value stream mapping is also nothing but a kind of process mapping. All of us have one way or other been into the process mapping thing, process flow diagrams. It is one of the 7 basic QC tools. Hope you remember what are the 7 basic QC tools as told by the Japanese in Toyota production system. Your process flow diagram, your scatter diagram, your cause and effect, and so on. So the most simple process flow diagram, whenever as professionals we try to understand what is happening in a process, we draw a process flow diagram or a process map. This is typically how a process flow diagram looks like. And it can be created for any business scenario. not only for manufacturing. For that matter, I have created this process flow diagram for a Amazon-like business setup, Amazon and Flipkart. So this is what happens, the customer, or for this typically I created for one of our customers who are supplying to Target Inc. of US. So what happens that Target of America have various big stores, just like IKEA has in various different cities. And then people kind of go and book their orders, and at times they pick up from the stores and so on. At times things get delivered to their homes and all. At times they go to the in-store service and all. So this is one typical process flow map. So the customer puts item in the cart, then customer selects in-store pickup, and then customer makes online purchase, then whether that is authorized. If yes, then it goes to this process stage. If no, then there is a decline message is sent to the customer and the process ends. If it is yes, then we display the success screen and send confirmation email to the tracking number, then place item in the awaiting store for delivery queue. Then we ask ourselves the question whether the item is delivered. If no, then we check the delivery date. If yes, then when send the delivery notification and so on. So this is one process flow map. Intentionally, I have taken a relatively complex, relatively different process flow map, because typically we see process flow maps in manufacturing setups. Raw material incoming, raw material checking, going to cutting, going to drilling, and so on. But I just want to emphasize that process flow maps are equally applicable, equally useful for any type of business scenario like this. So they are very useful. Still, they are not telling us what we really want to know, whatever we learned in last 1.5 hours. They are not telling us whether the operations are balanced. They are not telling us whether cycle time is meeting the takt time. They are not telling us what is throughput time. They are not telling us what is the lead time. They are not telling us which machines or which process need improvement. They are not telling us what shall be we doing to improve the performance of the process. For that matter, what comes into play is these fundamental concepts of lean, and then we will go to the value stream map. So some very fundamental concepts of lean are about value adding activities and non-value adding activities. Non-value adding activities are known as waste. Whereas there are certain value-adding activities. For example, welding flange onto the part, bolt part to the product, all those are value-adding activities. Then there are some non-value-adding activities, that is walking to get parts or wasting time or waiting time. And there are certain value-enabling activities or incidental works, that is, for example, pulling down the tool, unclamp and clamp fixtures. They are not really converting the product into something useful, but they are necessary but not really value adding. So primarily speaking, all the activities can be classified as 3 distinct categories. One, that is value adding activities. Another, non-value adding but necessary activities like clamping, unclamping, like inspection. And there will be certain non-value adding activities. So if we are able to identify what are the non-value adding activities or the waste, we shall be working towards eliminating those. Non-value adding activities shall be minimized and value adding activities shall be focused upon. So the focus of lean methodology is on eliminating the non-value adding activities. What is a value-adding activity and what is a non-value adding activity? A value-adding activity is an activity which physically changes the nature or shape of a product or service towards what the customer wants. Only that is a value-adding activity. Now, suppose this is a piece of metal. I want to drill a hole and customer wants a hole in this particular piece. So by the time this drill is removing metal from this piece of metal, drilling a hole, that only is a value adding activity. This activity, when I bring it up, clamp it here, move my tool from this mounting location in thin air till this is a non-value adding but necessary activity. And the time I lose in looking around and searching for tools is a non-value adding activity. So can we realize
even inspection is a non-value added activity, but
non-value
necessary.
adding activity? At times people say that it is necessary, but I do not agree. I say that if you can create
Produce a
such
high quality.
yes, high quality tools, jigs, fixtures, mistake proofing, then maybe inspection might not be necessary. But yes,
Necessary.
at times you can say that inspection is a non-value adding but necessary. But as the organizations mature, we will slowly realize that whatever we think is necessary can be either minimized or be thought as unnecessary. For example, suppose I have got this. Okay, this is a iron, and initially what I was doing, I was clamping it with 4 clamps and tightening the bolts. Then I realized that maybe I can have a magnetic locator and a stopper. So I just put it here and the magnet catches it, and I do not need anything. So that activity which I thought was non-value adding but necessary is now become a unnecessary non-value. I just bring this up, put this on table, a magnetic table, magnet catches it with a location. So no need to clamp. So as the organizations mature, you will slowly realize that whatever you thought initially or which were really necessary at that point in time can be slowly converted into identified as non-value adding activities. Similarly, the example I gave, so if I clamp my tool here 30 centimeters away, and this travel is, I think, is a non-value adding but necessary activity, but I clamp it just say, let's say 2 millimeters away, because this piece will require only a sliding difference. It will not require to move up and go like this. So this travel can be minimized and so on. If you're interested, I also have a course from Vision Excellence bucket on a lean champion, which is again a full 5-day course. So we can have a detailed discussions over there. But yes, right now it is important to understand that there is a distinction between the value adding activities and non-value adding activities, and certain activities are considered as non-value adding but necessary. And obviously the non-value adding activities have to be eliminated. Non-value adding but necessary shall be minimized, and value adding activities shall be optimized, and so on. So definition of value adding activities is the customer values it. It physically changes the condition or the nature or the shape towards what the customer wants. It is done first time right. If you are doing reworks and re-inspection and rework, it is again non-value adding, and it is the best available method as the time changes, the technology changes, of achieving the desired results. When I was young, like most of you, I used to go to bank to withdraw my salary, and used to spend half a day of my sick leave. Now that is not required. Whatever payments they give me come in my mobile phone. Whatever payments I need to make, I make through my mobile phone. No need. So at that point in time, it was necessary to walk up to the bank and fill up that form and take the cash. Now it is no more necessary. So there are 4 different filters through which we identify whether this particular activity is value adding or a non-value adding activity, and so on. So non-value adding activities are waiting, breakdowns, etc., etc., etc. So, and also there is 3M concept, which is called Muda, Mura, and Muri. So it is not only about the elimination of waste, it is basically elimination of the wasteful activities. So there are 3 types of wasteful activities known as 3M, that is Muda, Mura, and Muri. Muda means wastefulness or uselessness. Mura means unevenness or non-uniformity, and Muri means overburden. and so on. So therefore, in lean, we learn to eliminate all these wasteful activities, and all these become very apparent. And this is quick overview of the 8 wastes: transportation, inventory, motion, waiting, overproduction, overprocessing, defects, skills. So a popular acronym is steamboats, another popular now acronym is downtime, another popular acronym is wormhole. 8 big wastes that help us identify where the waste or wasteful activities are and how shall we be going and eliminating that. Now coming to lean specifically, this is the 5-step lean implementation methodology. Step number 1, we define value. Step number 2, we map the value stream. And therefore this VSM or value stream mapping is such an important core concept for lean and TPS. So what we are going to learn, and we have learned a lot about the core concepts, is about value stream mapping. Then we want to create flow. I also discussed certain points, how to create flow, then how to establish flow, then to keep pursuing perfection. So this is the 5-step lean methodology. This, my dear friends, is the value stream map. One of the value stream maps is here on your screens now. This is how a value stream map looks like, and typically there are 2 versions of value stream map. One is known as present state map and another is known as future state. So every time we do this VSM activity, first we create the present state value stream map, and then we create future state value stream map, and then we identify various initiatives and plot them on this map itself, and then we gradually move towards achieving the future state. Please note that the value stream mapping in Japanese books and literature is also known as material and information flow diagram. So when the Japanese people introduced this, they used to call it material and information flow diagram. When it was taken up by the Western countries, they devised a name known as VSM, and since value stream mapping is a rather less of a tongue twister than the material and information flow diagram, so it became very, very popular. Now, you can see there are 2 components, rather 3 components of a value stream map. One is the information flow. Look at this block. Another is a material flow, and another is a lead time ladder. These are the 3 core constituents of a value stream map. And whatever we have discussed today, all that is going to help us to realize that this is something very, very simple, extremely simple. How? This is how a value stream map looks like. What happens in a material information flow? Customer places an order that comes to your centralized production control or information processing thing. Then you, number 1, shoot out certain production directions or maybe some orders to your suppliers. Okay, so the information flow starts from the customer's end, comes to your unit. You process the information, some instructions go to the supplier, some instructions go to your manufacturing center. Simple. And then you keep tracking your production planning and production movement and all. So all that is your information flow. Very, very important. Information flow must also capture the specifications, the customer requirements, the timelines in which the customer wants them, the condition in which the customer wants them. So one complete block is that of information flow. Next block is that of material flow. Now we plot this material flow in a very typical manner. We plot just as we have seen in my last 1 hour or so, rather around 2 hours have passed now. Process A to inventory to process B. Process A to inventory bin to transportation to process B, to inventory to transportation to process C, to inventory to transportation or movement to process C, and so on. Yes, this is exactly how we kind of visualized all our processes. And this is exactly how this, my dear friends, is called a data box. A typical design. This is telling you the how many operators work here, only one. This is a symbol for the operator. What is the cycle time here? 300 seconds. Means this process A throws out one piece every 300 seconds. Yes or no, Ajay sir? Angaraja sir?
Yes.
This process cycle time is 300 seconds, means this process throws out one piece every 300 seconds. What is the changeover time for a shift here? 60 minutes.
60
But
minutes.
what is the average uptime? You have monitored it, let's say over 7 days, 9 days, 10 days. The average uptime is 80% of the time. It is working in 2 shifts, and therefore so many seconds are available at this process. Similarly, for the process B, how many operators are here? Ajay bhai? One. What is the cycle time? That means after how many seconds it throws out one piece?
45 seconds.
Yes. And how much time a particular piece spends on this process? 45 seconds, right? For 45 seconds, one particular piece is getting machined over here. Yes. For the process C, what is the cycle time? That is 300 seconds. That means that for 300 seconds, a piece is getting processed here. And also means that every 300 seconds, this machine will be throwing out a piece. So this machine will be throwing out a piece every 300 seconds. This machine is capable of throwing out a piece every 45 seconds. But will it be able to? No, it will not be. This machine is capable of throwing out one piece every 300 seconds. Yes.
Yeah.
And so on. So this is a data box. And this is the inventory symbol. So how many pieces I typically keep in this inventory?
Sir, influence of the number of resources. How many people are there? You counted. We are having one person per
There
process.
is some implication when we deep dive into this, because at times your cycle times can be greatly improved if you give one helper.
Okay.
Because otherwise, since with your basic intelligence, you said that, okay, one machine, one operator, but that operator was wasting a lot of time in picking things up, and since you want to
Non-value
maximize
adds.
the output of, and then you can work out, and typically it can be at times 1.2 operators or 1.5 operators, because one helper is catering to 2 machines and so on.
Good.
So,
Good.
and then there
Share
are
this.
cellular layouts. So that maybe there can be 0.75 operator per machine, because one operator is catering to 3 machines and so on. So do not get worried when somebody says that there is 0.5 operator per machine, because that operator is catering to 2 machines and so on. So as you improve the layouts and all. So there's some significance. So this, my dear friends, is called a data box. Now, we have understood this concept of cycle time. We have understood this concept of changeover time, the significance of uptime, how many shifts it is running, how many seconds are available, and so on. So based on this information, can I calculate with your help, my dear friends? Remember, this is a panel discussion, not a monologue. So let me calculate with the help of all the panelists, the throughput time first. Ready? Okay. So 6 days it takes from here. So for the calculation of lead time, production lead time is also throughput time. So 6 days lost here. Yes, for one piece. 6 days is spent in this transition. Then 300 seconds here. Then 4 days in this inventory. I am calculating the throughput time. Then 45 seconds here. 1 day here. 240 seconds here. 3 days here. So the production lead time is 6 days plus 4 days, that is 10 days, plus 1 day 11 days, plus 3 days 14 days. Yes or no? Cycle time, let me calculate. Cycle time, let me calculate. So 300 seconds 45 seconds, 300 seconds. For the whole pipeline, what is the cycle time? 300 seconds. Yes, one piece can come out of this pipeline only once the pipeline is full, only after every 300 seconds, not every 45 seconds. Remember that? Yes. And this particular piece is getting processed for how much time? What is the processing time? 300 seconds is spent on this machine. Then just waits and sits idle and sleeps. Yes. And 45 seconds here. And 240 seconds here.
585.
585. Is there something wrong when I say 300 seconds here and 240 seconds here? Yes, it is wrong. Therefore, can you see this?
Yes.
So if the data box says 300 seconds here, this shall also say 300 seconds. So somebody has intentionally made a mistake to check whether we are alert, or since it is 10 p.m. we are feeling sleepy. Okay, perfect. So coming back to this. So this, my dear friends, is how you can make a value stream. Now it is giving you all the necessary information. Yes or no? If I want to improve the lead time, that means reduce the lead time, reduce the throughput time. What is the focus area? I shall be focusing on these, and these. Where is the biggest inventory? Where is the biggest time lost? So if I want to improve the production lead time, this is where I shall be working, if that is the primary concern. If the primary concern is the rate of output, that is cycle time, then I shall say whether I shall work on this machine or this machine or this machine. Obviously, on the machine which is having the highest cycle time, I shall be working. And I shall also be comparing the cycle time with the takt time. Yes. So if you just for the sake of academic discussion, let's assume that instead of 300 seconds, this is actually 240. Okay. So this is 300 seconds. This is 45. This is 240. Where shall I focus my attention? On the highest cycle time thing. Yes. No point in spending time here, because this is what is my bottleneck. So yours, and then also I shall realize that if I have two operators here, and because of these two operators, cycle time is 45 seconds. Isn't it a good idea to move this one operator to this machine? So that even if this gets increased to 100 and this comes down to 200, it is more beneficial for me. Can you visualize that, sir? All of you, please confirm.
Yes.
That is where it helps. Because typically, just by historical nature, you are assigned operators because of their convenience. You are not really calculating. So now can you see the distinction between just plotting a simple process flow diagram like this and the complete MRI scan like this? Show me a thumbs up if you are clear about the benefits that this approach of VSM gives us. Till now, we are happy by drawing our process flow diagram, colorful diamonds, stars, and processing stages. But now this is giving us an X-ray and MRI of what is really wrong or what can be improved in our process. And this is a typical way of creating a process flow map, a VSM. So please note that there will be a present state and there will be a future state. There will always be three blocks, one for the information flow, one for the material flow, one is known as the lead time ladder. And we have understood all these concepts. I will not spend too much time over here. So this is the example we are seeing. These are the simple notations, the symbols. The process is denoted by this, customer supply is denoted by this. This is how data box looks like. This is how work cell looks like. This is a symbol for an operator. This is a symbol for material pull. This is a symbol for truck. Push arrow is like this. FIFO is like this. Load leveling is like this. Kanban post is like this. Today we do not have necessary time to discuss what is Kanban, what is pull system, what is push system. You people are interested, you can enroll for the Lean Champion course. But of course, these are very common concepts. So with this is exactly what we do. So let us try and calculate with the help of who is going to volunteer. Maybe Natarajan sir. In this example, Natarajan sir, let us calculate. First, calculate the lead time. Let's calculate the lead time or the throughput time. Okay, how we calculate throughput time? How much time it spends in the pipeline. So 2 days plus 5 days, 7, 7 plus 3, 10, 10 plus 4. So 14 days plus
14 days plus
1
9
hour
hours 2 minutes.
plus 9 hours. So 14 days plus 9 hours is my total throughput time. Yes or no? But my really processing time, it was getting processed only for 1 hour here. It was getting processed for 5 hours here. It was getting processed for 2 minutes here. It was getting processed for 1 hour here. So there can be very strange data. This is a data that is, let us say, coming from something where you need to cook it in an oven, in one of the manufacturing facility. So this 1 hour was the material preparation time or the casting time when you poured this into a die. Then you allowed it to cook in an furnace for 5 hours. Then it just took 2 minutes to really unload using a robot. Then it took 1 hour to cool down. Then it took 1 hour to hand paint. Can you see? So this is how this gives us you a complete overview of whatever is happening. So the cycle time will be decided by what, which is having the highest cycle time of the whole process will be by the highest cycle time, which is the 5 hours here. So this is how typically a data box looks like. Yes. And another similar example, and then another similar example. So this is how you create a value stream map. There are typical steps. Step number 1, you start from the customer end, and then you move backward. Step 2, step 3, step 4, step 5. I shared this with you. All that we have discussed. No, nothing to worry. I'm just quickly running through all this. All that we have discussed in great detail. So I'm very sure that you have understood all these, no problem. And then this is what we have present state. So this is my present state. Then let me see what improvement I can make. So I will spend another 4 or 5 minutes on this, then we will be done with value stream map. If this, my dear friends, is my present state or the current state value stream map, let us have a look at this. Obviously, as I discussed, there are 3 blocks. One is for information flow, one is for material flow, and one is your lead time ladder. The information obviously is flowing from the customer to the production controller, from production controller is flowing to the supplier, then it is coming to the material flow. So this is where the lead plates manufacturing. Then this is where at this process stage number 2, plates curing and drying. Then material is moved to the battery assembly. Then the material is moved to the battery charging. Then material is moved to the shipping. And between all these process stages, there are inventory. Now let us create the data boxes. For the this cycle time is 4 hours. The lead time is 6 hours. What is C&A? C&A is complete and accurate. What we call as yield, percentage of yield. So we have created data boxes for all this. Here, can you tell me how many operators are there? 4 operators. Here 4 operators. Here 2 operators. Here 2 operators. Here 2 operators. and so on. So if I calculate, can I make my lead time ladder here? Yes, I can make. So 4 hours is spending here, then 6 hours is spending in waiting, 26 hours it is spending here on processing. So this is how I can calculate my lead time. Then I identify certain improvement activities. So can we avoid unnecessary transportation? Can we reduce the defects here? Can you see here? So here the yield is 97%, 98%, 98%, 100%. Here the yield is 92%. So we must focus our attention here so that the yield can be improved. Similarly, this 26 hours is too high. It is not letting things balanced. So we must focus our attention here. So can you see, when you draw this map, it is not only telling you what is happening, but it is also telling you where we need to work. Okay, and that is how we plot this as improvement opportunities. So one improvement opportunity is here, reduce the defects. One improvement opportunity is here. We saw that why it is taking 26 hours for plate curing and drying, because of unnecessary transportation of the plates. Here also we identify, so the welding machine uptime can be improved, because you can see the uptime was a challenge. Okay, and then once we achieve that, so from 26 hours it was brought down to 10 hours. From 92% it was brought up to 98%, and so on. And therefore now it is a much more balanced and more likely to meet the customer demand. This is how your things happen. And if you want to have a look at some real life examples, how this actually happens, visit my LinkedIn profile. I keep conducting value stream mapping, and I keep posting articles and photographs of those, and I will be sharing maybe a couple of them with you. So then you plot all this on a Yamazumi chart. What is value adding, what is non-value adding, and based on that you realize that okay, this is the particular operation which is not meeting the takt time. So you identify what are the non-value adding activities, and then you reduce the cycle time over here. So that was kind of a comprehensive coverage. I would just like to take you to my LinkedIn profile. Let me share a couple of examples. Just quickly searching the post about the value stream mapping. Yes. Okay, so this is one of the examples where we are doing our value stream mapping. So we need a big wall, then all these are your data boxes, and then we have plotted the whole process here. And then we discussed, this is how we created the location for doing your value stream map. So this is how you identify improvement opportunities. So all this is real life. All this is real life. There is nothing that is just theoretical. I just wanted to show you these photographs. Everything captured in great detail. Then we this is how you identify opportunities and all. Okay, so that is all that I wanted to discuss today. Thank you very much for being such a participative and patient team.
Thank you, sir.
So that
Thank you very
kind
much.
of gives me great pleasure to say that today also we had a very engaging and fruitful discussion where we understood the core concepts of value stream map, the vocabulary, and then we realized in the later sections of the discussion that why the value stream mapping is a much more useful tool than your regular process flow diagrams. So thank you very much for being such a nice team here. And I would like to quickly understand some feedback from some of you. If you want to give me a quick feedback.
Yes, sir.
The data blocks you have shared, actually, I think that's quite helpful, when you compare with the PFD to, the information flow, material flow and lead time flow there. The data blocks in the material, flow. I think that's a real helpful.
Exactly.
If
The
you
data
map
blocks,
that, I think, yeah, you are creating a data.
data blocks as well as your lead time ladder. They give
Absolutely.
you the deep insight into what is happening in the process and what needs to be improved.
Yes,
Very
sir. I think this is an excellent way of explaining the things because actually this is a coaching. So you are getting the feedback in between.
No, it is a panel discussion.
No, sir. It's you can call the panel discussion, but it's a coaching where you're taking the feedback also. And the thing is, we understand whatever you want to deliver. This is the good thing. The way you are explaining, the clarity, the time, 10 types time. A lot of people are confused. Even in the management cadre, people are confused. So this is very good way of understanding. Thank you very much, sir. Thank you for being there.
Okay, so thank you, friends. Good night. We shall call it a day. Okay,
Good night. Thank you so much. Thank you.
Thank you, sir.
Thank you, sir.